In this tutorial, we're going to explore the characteristics of radio waves. So imagine that we have a transmission tower for radio station KXWT, and they're emitting radio waves from the top of the tower like so. Try as I might, I was only able to draw this in 2 dimensions, but you can imagine that in real life, a radio wave like this also distributes its power in and out of the screen, right? In real life, it would be propagating through 3-dimensional space, so we'll have to take that into consideration. Now, if we zoom out a little bit, and you see yourself over there on the right, the radio wave will eventually intersect you, and we're assuming that there's no reflection off of the ground or objects or anything like that. There are some logical questions we will want to answer about the radio wave that hits you. One is just, what is the wavelength of that wave going to be? So what is the value of lambda? Another is, what is the time delay between the time that the radio wave is transmitted from the top of the tower and the time it reaches you? And the final question is, what is the intensity of that radio wave at your location? To answer these questions, we need a few more details, the first of which is the distance between you and the radio tower. So let's say that that distance is 4.50 kilometers, obviously not to scale. The nice thing is that's a far enough distance that it doesn't really matter whether we're measuring from the top or the bottom of the radio tower. We'll also need to know the frequency at which this radio station operates. Let's imagine that it's 105.5 on your FM dial. Well, that means that its frequency is 105.5 megahertz. We'll also need to know the total amount of power coming off of this radio tower. Let's say that that's 75 kilowatts. We'll also need some equations, such as the one that relates wave speed to wavelength and frequency, the equation for the intensity of a spherical wave, which this one certainly is, it's going out uniformly in all directions, one of the equations of motion, and of course the value of the speed of light. Remember, although you listen to radios, radio waves are a type of light, meaning that they move at approximately the speed of light in air. Okay, so let's rearrange everything and start by calculating the wavelength of this wave. To get the wavelength, we can use that v equals lambda times f, realizing that the numerical value of v is just going to be the speed of light. So we can substitute in c, rearrange to solve for lambda, and then put in the numerical values of c and f. So we do that and rearrange a little, and you see in this particular example the numbers work out nicely because the powers of 10 to the 8th cancel, so that means that lambda is just going to be 2.84 meters. So that's the wavelength of this particular radio wave, and you can see that the wavelength is a little bit bigger than a person. That's one advantage of using radio waves to communicate, is that their wavelengths are typically large enough that they don't scatter appreciably off of small objects. Okay, so we figured out the wavelength and we'll put that over on the left. Next question. How long does it take the radio signal to go from the tower to you? For this, we'll use the equation of motion. You can see that this is going to simplify considerably because one of the defining characteristics of light is that its acceleration is 0, meaning this whole term on the right is going to be 0. That means that the displacement of the wave in the x direction is just going to be equal to its speed times delta t. Well, that's pretty easy for a light wave. That means delta x is just c delta t, and now we can just solve for delta t. So delta t equals delta x over c. Delta x just equals what I described using the variable r, 4.5 kilometers, that's the distance between you and the radio tower. So we can put in that value, put in the speed of light, get our units right, and delta t comes out to be 1.5 times 10 to the minus 5th seconds. That's 15 microseconds. That's why, generally speaking, you don't notice a huge delay when communicating using light on Earth. So we'll record that value on the left. The final quantity we want to calculate is the intensity of radio waves at our location. So for this, we'll use I equals p divided by 4 pi r squared, and I'll remind you that the 4 pi r squared term comes from imagining that the power has to be distributed over the surface area of a sphere of radius r. So in this case, that imaginary sphere would be centered on the radio station transmission tower, and r, the radius of that sphere, would stretch out to our location. Alright, so knowing that, we can insert the value for the total power of the tower, namely 75 kilowatts. We can insert r equals 4.5 kilometers. We need to be careful with our units, convert kilometers to meters, and then do all of the math to see that the intensity comes out to be 2.95 times 10 to the minus 4 watts per square meter. The units for intensity are watts per square meter. So what does this number tell us? Well, let's assume that a person's cross-sectional area is about 1 square meter. That's probably a slight overestimate for most people, but it's not off by more than the factor of a few. Well, if that's true, and if a person can perfectly absorb radio waves, which I already said is not a guarantee, Then, if you were located 4.5 kilometers from a tower that transmitted using 75 kilowatts of total power, you would only absorb a power of 2.95 times 10 to the minus 4 watts. A minuscule amount of power, not enough to do anything with. This is why real radio receivers are generally hooked up to amplifiers, so that you can actually take that really weak signal and turn it into something that you could ever listen to.